I have to admit, I don't love the magic formula myself personally, because I have a messy brain, and my messy brain sometimes loses track of who is M1 and who is M2, who is V1 and who is V2. And I put the things in the wrong places, or I write down the wrong formula. And so for me, this is not the most effective method, but some people love it, so I will teach it to you, okay? Because if you're good at keeping track at what goes where, then this can be a really simple way of doing all dilution problems, except for mixing two solutions of the same chemical. And this takes advantage of the fact that, what do you get if you multiply molarity by volume? You get moles. And what do you know about the moles before dilution and the moles after dilution? They're the same. Oh, look, so moles before equals moles after. Yes? So that's all it comes down to. And what it means is that you can just chuck numbers into this formula and then you're good to go. I don't even know why I have this first example, because it just shows us how we've been doing dilutions to this point, okay? Because it says, okay, here we have our initial volume and our molarity. And so we find our moles. Whoa, what happened there? So we find our moles. Oh my goodness, having so many challenges today. Okay, we find our moles. And then to it, we add some water. So we say, all right, we found our moles, and now we're going to, so step one, find moles. And then step two, find the total volume. And then step three, you take your moles and you divide by your total volume. That's the method I like to use because it makes sense to me and I don't have to remember things. Yes? However, let's take a look at our magic formula. It takes advantage of the fact that moles 1 equals moles 2. The moles before dilution is equal to the moles after dilution. So basically M1V1 equals M2V2. You will see if you use Hebden at all, he writes it as C1V1 equals C2V2. What do you think C stands for? Concentration. Okay, so it's the same formula. So if you do like to use Hebden as a source of extra practice problems, you'll just see that he uses that instead. Okay. This is great for dilutions with water. You can use it for mixing two solutions of the same compound, but I will not be covering that this year. So this M1V1 M2V2, I'm not going to cover that. But if you're like, I love M1V1 blah, 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 you can learn it in Hebden on page 101. So if you're like if you're discover that you're like, this is my method, this is the one I love, you can mix two solutions of the same chemical. Hebden will show you how to do it if you don't pick up on it just naturally yourself, okay? But I'm not going to teach it. So here we have a question, and the tricky part of this is just to realize who is M1, who is M2, who's V1, and who's V2. First thing is to realize that this is all referring to the same thing. Yes, we have 15 milliliters of 1.50 molar. So those are going to be either a 1 or a 2. And quite frankly, it doesn't matter whether you call it 1 or whether you call it 2, as long as they go together. They both have to be 1 or they both have to be 2. Now, I'm going to call them 1 because it has some water to it, added to it, and then later we have something else. But like I said, it doesn't actually matter. So here what we have is we have V1 and we have M1. We have some water added. Oh, so we don't know our volume, yes? But it changed the concentration to not V2, M2. See, this is why I don't like this method, because I will write the wrong letter, I'll write the wrong number. This is M2. So now what you do is you can, oh, I've just written that there. You will just take your M1V1 equals M2V2, and you'll say, I don't know what V2 is. So I'm going to solve for V2. So V2 is, I'm going to take my M2 and move it down here. So V2 is equal to M1V1 over M2. Then you just go grab your numbers and you say, what was V1? V1 was, or M1, 1.50. What was V1? 15 milliliters. And you can leave it in milliliters because your answer will be in milliliters. Okay, and what was my M2? It was 1.15 molar. The molars cancel out and you are left with milliliters. Yay, the units worked. If the units don't work, you've done it wrong. Okay? Now, you might say, oh, great, I am done. But what does the question ask us for?
Volume added.
The volume added. Is this the volume added? No, this is the total volume, yes? So we had our original volume, and then we added some water, and we got our total volume. How will we find the volume of water added? Yes? Final volume minus the initial volume. So we're going to take V final minus V initial. That's our final volume. Our initial volume was the 15 milliliters, and we get 4.6 milliliters of H2O was added. And this is a type of dilution question that we haven't done. I haven't asked you, what's the final volume? I don't know why you would actually do that in practical real life. Do you know what I mean? But it's a question that can come up in chemistry. That's why I don't tend to spend that much time getting too wound up about it. All right, let's try example 1 again. This is what is our resulting concentration? And if our resulting concentration, that's going to be M2. Okay, so that's what we don't know. We have 125 milliliters, that's V1, of 3 molar, that's M1. It has 38.5 milliliters of water added to it. So our total volume, V2, is 165 milliliters, and M2 is what we don't know. And if I were actually doing this and I had highlighters, I'd probably be color coding for myself so I didn't mess up. Yes, because I do tend to suck at that quite badly. So I'd be like, okay, M1V1 is equal to M2V2. So I need to have and I solve for M2, V2's on the bottom, and M1 and V1 are on the top. And I'd be like, okay, I'm plugging my yellow things into the top, bam. And I'm plugging my green thing onto the bottom, bam. Yeah? But I don't know. Like I said, if you have a good mind for keeping things in their correct places, you should be fine. I just don't. I know that about myself, so I don't use this much. And there you go. Cross out your milliliters. Milliliters cancels with milliliters, and we end up with molar. Is good? Okay. This is a question very much like what we did yesterday in the mini lab. Yes? How much of the 4.00 molar NaOH, so this would be our stock solution. Okay, so that's our concentrated solution that we're going to dilute. And we want to know how much. So V1 is what we don't know. M1 is 4 molar. And we want to make 175 milliliters of 0.5 molar. So V2 is 175 mils. M2 is 0.5 molar. So we would solve for V1, M2V2, and this time my green stuff is on top, yes? So I'd be like, okay, green goes on the top, yellow goes on the bottom, plug it in, solve it, and I get 21.875 milliliters. I don't know why there's a second milliliters there. I need to fix that. Fix. What would you use to measure out your 21.875 milliliters? What might be a good choice to measure that out? Pardon me? You could use a graduated cylinder. Any other choices? Do you think it is likely that we would find a volumetric pipette of that volume? No, because it's not a nice round number, but you could use a graduated pipette. If you really had to be very precise, you could use a burette. Yeah? And the reason I want you thinking about this is I want you to think about, now here I have 3 sig figs, right? But what if I had 2 sig figs? Let's say I had 0.50 molar times 175 mils over 4.0 molar, and I got 22 milliliters with sig figs. Would it make sense if I had my graduated cylinder? That doesn't look anything like a graduated cylinder, but you're going to pretend. And let's say that each individual little marking is 0.1 mils. Okay, so this here would be 21.9, and this would be 21.8. Yes? Would it make sense to use this cylinder to measure 22 milliliters when our actual answer is 21.875? Would that give us our best result, our most accurate result? No. Even if I only have 2 sig figs here, you need to say, okay, sig figs aside, sig figs is good for figuring out how accurate it is, but if I start using a rounded off value to actually make a solution, that's kind of useless, yeah? Because I don't want to be creating error in there. I want to get as close to 21.875 as possible. So I would probably be like right here. So when you're using your numbers to come up with something you're going to measure out, go to however many digits your measuring device will allow. Does that make sense? You're not going to be like, oh, I'm going to round it off because I only have 2 sig figs. You know, it's not going to be as good of a result. Yeah? That's a practical point. On a paper and pen test, you're probably never going to run across that. That's just for like lab stuff. Yeah? Okay. And now you're not going to read steps to make the solution. You are going to tell your partner how to make the solution without looking at the steps. Try to remember from yesterday. Describe it to them. Pantomime it. Show them what you would do. So let's assume I'm using a graduated cylinder, and I take my 4 molar NaOH and I pour it into the graduated cylinder, and I get 21.8 milliliters or whatever it is. Okay. What do I do with it now? Oh, I've measured out my volume of 4 molar. I dilute it with water in here. Yes. In a volumetric flask, do you think it's likely I'm going to find a 175 milliliter volumetric flask? Yeah. No, your choices at this point would be like, scrap that idea. I'm not making 175 milliliters. I'm going to make 200 milliliters because they make 200 milliliter volumetric flasks. Oh. Or if you're like, I've already done this calculation, I don't want to do another calculation, you can grab yourselves a 200 mil graduated cylinder and make the solution in here. So I could be like, okay, here's my stock solution. Glug, 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 glug. What's on the sides of here now? NaOH. Do I want that NaOH in here? Yes, I do. So I'm going to rinse it out. Rinse. Yes? And then what will I do? Add water to which line? 175 milliliter line. Next. Parafilm. Invert to mix. And we're done. Yes? Okay. Good stuff. All right, there are some exercises here. We're not going to do them right now. You'll have a bit of time later on. You can choose what order you do the homework questions in. This is the M1V1 M2V2, so you can choose whether or not you want to do that, okay? This one, you're going to do only odds, and the number 3, the key is wrong. But this is the next one. Here we are, ion concentrations. I asked this morning's block if they had looked at ion concentrations. It was for homework at some point, but I feel like maybe nobody did it.
Wait, 8.3 up?
Yeah.
Wasn't there another one?
There were a couple of questions about ion concentrations. We're just going to go over this to show you how to show the work. This is super easy. You've done stoichiometry. you can do this, okay? So if we have sodium carbonate, Na2CO3, and if its concentration is 0.25 molar, and this is on page 78, what is the molar concentration of each ion? What that means is you need to identify the ions. Who are the ions? Na plus and CO3 2 minus. And the best way of doing this consistently is to write your, what equation is this equation here? That is our balanced dissociation equation. Okay, so we write our balanced dissociation equation. And then we say, well, here's what I would do, because this is my favorite method. I would write underneath here, I'd be like, oh, if this is 0.25 molar, then the carbonate will also be 0.25 molar because they both have a coefficient of 1. And what would the concentration of the sodium be? 0.50 molar. And that's all you would have to do. Yes? However, depending on how intuitive this is for you, you can choose other methods of showing your work. You can use the particle ratio or you can use the mole ratio. So if you're having any trouble, if you're like, I want to double it, or if you've got like a weird 2-to-3 ratio and you're not sure, should I multiply by 2/3 or should I multiply by 3/2? This can be helpful, okay? Here's how you would show it using the particle ratio. Concentration of Na. We'll start with our concentration of Na2CO3, and because we've got that, we need to cancel it. And we know we have 2 Na pluses for every Na2CO3, and that gives us 0.5 molar. Yes? You can use the mole ratio. And the only difference in there is you write the word mole. Right? We've got a 1-to-1 relationship here. We're still canceling Na2CO3. In this case, the moles in the molarity cancels with the moles down below, but you get moles back at the end, so you still end up with your molarity. This is what I just did, where you write the dissociation and underneath you write the concentration ratio. This line here that just shows that it's a 1-to-1 to 2, you do not need to show that line. Okay, it's just here for the purpose of being in the notes. Oh, it's a 1-to-2-to-1 ratio. Oh, look at that, okay. Or if you're like, wow, all of those just seem like way too much work, you can just be like, okay, I know that I have 2 NAs in every Na2CO3, so sodium will be twice as concentrated. So I'm just going to take Na2CO3 n times by 2. Yeah? And I know that there's only 1 CO3, so it'll be the same as Na2CO3, so it's just 0.025. Any of those are acceptable ways of showing your work. Pick the one you like. Like I said, if you've got a 3-to-2 ratio and you're not sure whether you're multiplying by 2/3 or 3 or 3/2, then that one in the middle where you use the mole ratio is usually good. Okay, we're going to, don't look at the answer. No, you can look at the answer, it doesn't matter. Anyway, if we have iron 3 nitrate, and if nitrate is 1.20 molar, what is the concentration of iron 3 nitrate? Could you fill that in just by looking at it? What would it be? 0.0 0.400 molar. And iron would also be 0.400 molar. So that's sufficient. That's all you need to do. You can again use the particle ratio or the mole ratio, or you can just be like, you can write out all the concentrations and, you know, divide by 3. You don't have to show that work though. If you want to, you can. Or you can just be like, I know that the concentration of FeNO3 is 1/3. Done. I don't know. You can kind of do those in your head mostly. There are some exercises here. They involve, we start off easy by giving you the molarity. In number 3, we give you moles and milliliters and ask you to find the each ion. In number 5, we give you grams and milliliters and ask you to find each ion. In number 7, we give you the chloride ion concentration and ask you to find the original thing. Number 9, we do a dilution and then ask you for the ion concentrations. And number 11, oh boy, how many grams of Al2SO4 are there in the solution? So they're all different. Every single odd question is different. Every even question is another version of the odd question. So if you do all the odds, you'll have covered all your bases. If you want more practice, you can do the evens. We're going to take a break from me teaching for now so that you guys can do a little practice on this. Like I said, you can start with page 77 or page 80, whichever one you want. And then we'll finish up the class with ionic equations. Yes. Yes. Okay, friends, we are going to take a break from calculating, and we're going to go to page 82. And we have already written equations for double replacement reactions. So here is an equation. NaCl plus AgNO3, both are aqueous. Give us the products NaNO3 aqueous plus AgCl. This is on page 82. And because we have written the formulas, this is what we call the formula equation. And because that's a long thing to write, we can just write FE, formula equation. The problem with the formula equation is when we write NaCl, it looks like the Na is together with the Cl. And the AgNO3, it looks like the Ag is together holding hands with the NO3. Whereas if we actually look what's happening in the beakers, the Na and the Cl are freely floating ions. In other words, they are dissociated. Just like the Ag and the NO3, they're not actually together. They're not holding hands. So what we're going to do is we are going to take our NaCl aqueous, and we're actually going to write it separated. So every time we have an aqueous substance, we will separate it into its component ions. So far, so good? Okay. Our AgNO3 is aqueous. So we will separate it because it is separate. Now our products, if we look at our products, one of the products is NaNO3. And if we go back up to our beakers, and don't worry, I'll move this back down again. If we go back up to our beaker, is the NaNO3 together or is it apart? It's apart because it is floating freely. On the other hand, the AgCl is our precipitate, and the little Ags and Cls are holding hands. So they are actually together. So we're going to reflect that in our equation here. We're going to separate the NaNO3 aqueous, but we are going to keep the AgCl together because it is not separate. So this is a more correct representation. It's long and it's awkward, but it is a more correct representation. And because it contains all of the ions, it is complete. Therefore, we call that format the complete ionic equation, or the CIE. So basically, in a complete ionic equation, you take anything that's aqueous and you split it up. You take anything that's solid and you leave it together. Liquids will also stay together because, like, if you look at water, water does not dissociate, right? Now, if we take a look at our substances up here, is sodium actually doing any reacting? How does it compare to how it was before? It's exactly the same. So sodium is actually not reacting. How about chloride? Is chloride reacting? Yes, it ends up not being up there anymore. It ends up being in a compound with silver chloride. So the silver is also reacting, but the NO3 is also not reacting. So we can simplify our equation into including only the things that react. So in other words, only the silver and the chloride end up reacting. So we can write it with only the things that actually react. And who are those? Those are the silver and the chloride. And so we just write Ag plus Cl minus gives us AgCl. And because we've taken our equation and we've simplified it down, we've gotten rid of anything that cancels out kind of on both sides. We call that the net ionic equation, or the NIE. And it is possible to go from the complete ionic equation to the net ionic equation by looking at your complete ionic equation and saying, what does not change from one side to the other? Well, sodium stays as Na+. That has not changed, right? NO3 is staying as NO3. Those have not changed. But the silver and the chloride, they change into AgCl solid. So what you can do is you can identify the ions that are not reacting, and you can just cross them out. Just like in math, if you've got something on one side, you can cancel it with something on the other side. Let's say you went to a baseball game, yes? And who do we call the people who go to a baseball game but don't actually play the game? They just watch it. What do we call those people?
Spectators.
Spectators. So what do you think we might call these ions that are not participating in the reaction, they're only watching it?
Spectator ions.
We call them spectator ions, okay? And I think we've actually got that on the next page here. Na and NO3, they're just floating about watching. Woo, what happened there? That was not good. Watching the Ag and the Cl react. And the people who watch, those are our spectators, and therefore these ions are known as spectator ions. And you can see they're the same before as after. So sometimes you will be asked to write the formula equation and the complete ionic equation and identify the spectator ions and write the net ionic equation. So that would be like the whole meal, full meal deal, okay? So we are going to do that for iron 3 nitrate and potassium carbonate. So iron 3, this example is there, but I'm going to do it separately so you can like watch the process. 3 nitrate, you can choose if you want to cover it up, you can do that. You guys are now good at writing chemical equations. Could you write a chemical equation for this, the formula equation? Let's start by writing the formula equation. You try, and then you can check with what I've got up here.
They are both aqueous. Low-key chemistry is kind of interesting. Why are you taking chemistry? I was gonna take Why? Wait, cars just eight bars. I'm recording it.
Okay, so we have Fe, NO33, plus K2, CO3, aqueous. If you've got the formula equation, you can go ahead and try the complete ionic equation, identifying your spectator ions and the net ionic equation. Yes? Yes, actually, we should maybe do that together because we do have to talk about subscripts and coefficients. Okay, so we would end up with Fe 2 CO3 3 plus K NO3, and we need 2 Fe's and we need 3 CO3s, which means we need 6 of those. This is our solid, and that one is aqueous. So for our complete ionic equation, we do need to consider both the coefficient and the subscript. So for the iron, there is no subscript, so it's just 2. So we're going to have 2 Fe. And what have I missed? My charge. So that's going to be a 3 plus. Aqueous. Now, I need the coefficient and the subscript for nitrate. So that's going to be 2 times 3 is how many nitrates? 6 NO3s. For our potassium carbonate, we have a 3 as a coefficient, and the potassium has a subscript. So that's going to be 3 times 2 is 6 K pluses, aqueous, plus, now remember that little 3 at the bottom there? That doesn't mean there's 3 carbonates. It just means 1 carbonate. So we're going to have 3 times 1 is 3 carbonates, CO3, 2 minus. And complete ionic equations are a pain because they're so long, I usually can't even fit them on one line. So often what I'll end up doing is I'll be like, okay, and now here come my products. This is a solid, so what do I do with it? Leave it as is. Fe 2 CO 3 plus 6 Ks and 6 NO3s. 6K plus 6 NO3 minus, it's supposed to be a minus, aqueous and aqueous, and this one is a solid and that one is aqueous. At this point, you say, who are my spectator ions? K and NO3. Because they've not changed. I do want to draw your attention to this because this is a place where people sometimes make mistakes. Not 6K plus 6 NO3 minus. Why is that incorrect? Coefficients. If I'm identifying spectator ions and I say 6 Ks, that means only 6 of the Ks in the entire reaction are spectators. Is that what I want to say? No. So we don't do that. We do not want any coefficients. No coefficients. We also do not want to write K plus plus NO3 minus because that looks like a reaction. You can write a comma, you can write and, doesn't matter. This looks like a reaction. So not that either. And that leaves us with our net ionic equation. And you can do that by canceling out your spectator ions, and you are left with 2Fe3 plus aqueous plus 3CO3 2 minus aqueous gives us Fe2CO3 3 solid. And we do have 2 minutes left, so I am going to mention to you that there is a shortcut. If you are not asked to do the whole thing, wouldn't it be nice if you did not have to do all of this if you are only asked for the net ionic equation, right? Like, because that looks like a lot of work, yes? If you go and you say, who is my precipitate? You can say my precipitate is that one. That's the only thing that's going to be involved in the reaction. So my product is going to be Fe2CO3 3. Who do I need to make that? I need only 2 Fe's and 3 CO3s. And thereby I have now skipped all of the complete ionic, identify the spectators, blah, 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 blah. I just said, who is my solid? Who do I need to make that? And that's my net ionic. Yes? And that saves you some stuff, unless you're, of course, asked to write the complete ionic, in which case you got to do it, right? So there you are. Alrighty. Homework. There's no ionic equations on the homework. Homework is here. Yes?
Since a precipitate, it has to be a solid or a liquid, right?
A precipitate is a solid. Only a solid. Now, if you're writing a net ionic equation and you've got an acid-base reaction, your liquid will act the same way. It stays together. So that's going to be your actual product. So when you're writing the net ionic equation, that will be your product, and you'll write H plus OH gives water.
So then like solids and liquids would stay the same, but all the
Aqueous come apart. Yeah. Solids and liquids stay together. Aqueous come apart. Yeah. Hi.
For this one,
Yep.
so that is AlCl3, right?
Yep.
So if I'm creating a product, it will be Cl2, but then
No.
this Cl minus is an ion, so I have to treat it as an ion
That's
instead
right.
of a gas.
That's correct. Yes.
Okay.
Yeah.
So every single time I see like a diatomic, it's like that. I don't put two here.
When it's in an ionic compound, it's not Cl2,
Ionic, right? Okay.
right?
Yes,
Because
yes.
it's already got its
Yeah.
complete shell. It doesn't need to
Need
pair
another
up
one, yeah.
yeah.
So it's ionic compound, no two.
Correct. Correct.
I think graduating is international.